Hey guys and gals, this is the third video in the series for ionic compounds. This video we're going to focus on the names and formulas of compounds, and we've already touched on the names somewhat when we discussed monatomic ions and how to name those. For example, our cations. Say if we have calcium, +2 charge, we simply say the name of our cations. So it's a calcium ion. As opposed to our anions, if we have a negatively charged ion, bromine as an ion. Remember we dropped the ending and add an IDE, so we have a bromide ion. We then progress from there to talk about binary compounds. And a binary compound is made up of two monatomic ions, such as sodium. There's one cation plus chloride ion coming together to form a compound sodium chloride. So a binary, the bi refers to the fact that there's two ions going on there, two elements. Okay. Now, we can't get this confused with scenarios like this where we have a magnesium with a +2 charge and chlorine. Now, this magnesium, because it's a +2, remember we're going to crisscross that to get the compound magnesium chloride, Mg2. Now, this is still binary, even though there's 3 ions in this compound, but there's only 2 elements at work here. So this is still referred to as binary. Okay, and I also want to refer you back to the polyatomic ion list, and on the left side of this list is where we see our nice list of the monatomic cations and anions. Okay, so they're listed with their charge. Okay, so moving on. Hold on. Getting some technical difficulties here. I'll pause and reset. Alright, sorry about that. I had to adjust. So we're moving from binary compounds that are made up of 2 ions to now we're going to discuss polyatomic ions. So it's not monatomic with 1 ion or binary with 2. These are polyatomic ions. Now, polyatomic ions are ions made up of more than 1 element. What's very, very, very important to keep in mind with polyatomic ions, these ions will always act as a single group or a single unit. Okay, so I want to refer you back to our polyatomic ion list over here. So notice these ions, there's more than 1 element that has already bonded together and formed an ionic compound here, but it's not binary. Okay, and notice there's only 1, well, there are technically 2 on this list, 2 positive polyatomic ions, but the only one that we will really work with and that you'll see is ammonium here, NH4 with a +1 charge. Okay, so just take a peek at all of those, and the ones that are in bold are the ones that are the most common, and you'll learn to just kind of know those by nature as you are working with these. Alright, so back to our notes. So some of the more common ones that we see, we refer to these, well, let me back up before I say that and say that there is really one major polyatomic cation that we mentioned there, and that is ammonium, which is NH4 with a positive 1 charge. So what's taken place here is there's already been a reaction that's taken place between a nitrogen atom and 4 hydrogen atoms. And in that process, a compound has been formed, and that total compound has a positive 1 charge. So that charge is associated with the entire compound. Okay, so that is ammonium, and that is the only polyatomic cation that we worked with. So what that means is this is the only one that has a positive charge. So now, when we go to the anions, we're going to find that the vast majority of these are what we group in a group called oxyanions. And all that means is that these are anions containing oxygen. Okay, so let's go back and take a look at that list and look at all of those. Look at all of the polyatomic anions that contain oxygen. So these are all of the oxyanions. Really, the only exception to the oxyanion thing is cyanide. And cyanide is just kind of one of those weird exceptions that we run into sometimes. So notice the vast majority contain oxygen, so we call them oxyanions. Alright, so let's talk about some of these. What we encounter when we're dealing with oxyanions is most of our nonmetals, back up and say most of our nonmetals, have multiple oxyanions associated with them. For example, if I'm looking at the nonmetal of nitrogen, nitrogen forms 2 oxyanions. It forms an NO3 that has a positive 1 charge, and it has an NO2 with a positive 1 charge. Okay. Now, referring back to our list here, we see that NO3 with a negative 1 charge is called nitrate. Whereas NO2 with a negative 1 charge is called nitrite. Okay, so you might already be seeing some differences in the naming here with these polyatomic anions. Nitrate and nitrite. So notice here that none of these end in an IDE like we encountered with the monatomic anions. So we do not use the IDE ending for the polyatomic anions. Okay, so some other examples here. Let's look at phosphorus. Phosphorus forms 2 oxyanions. It forms PO4 with a 3 negative charge and PO3 with a 3 negative charge. And notice the charges are always the same for the element that has these different oxyanions. Okay, so PO4 with a 3 negative we see is named phosphate with an ATE, whereas PO3 with 3 minus gets phosphite with ITE. Okay, so you may already start to see a pattern developing here with the way that these are named. And here's that pattern. This is how we name polyatomic anions. The naming rules for polyatomic anions. Simple as this. The one with the most oxygens, or the greater number of oxygens I should say, always ends in the ATE. And then the one that's less ends in ITE. So if you have one less oxygen, it ends in ITE. So back up here to phosphate and phosphite. Notice PO4, there's 4 oxygens here, as opposed to PO3, 3 oxygens. So obviously PO4 has the most oxygens in comparison. So it gets the ATE ending, phosphate. Whereas the one that has one less, PO3, ends in a phosphite. And we see that back here when we looked at, if I can back it up a little bit. Got some more difficulties. Hold on, I'm going to pause. Be right back with you. Okay, sorry about that. I had to restart the notes program. Okay, so what I was mentioning was the fact that we have this. Alright, sorry about that. I had to restart again. Okay, so back to the naming rules. The one with the most oxygen gets the ATE, the one less with the ITE. So phosphate with the 4 oxygen, phosphite with the 3. We see this again when we were looking at nitrate and nitrite. So ATE here gets the NO3 with the 3 oxygen gets the ATE, while the NO2 with the lesser number of oxygen gets the ITE. So we see this on our polyatomic ion sheet here. Notice all of these different variations. So here we see sulfur. Sulfur has 2 oxyanions, SO4 with the 2 negative charge and SO3. So notice again the one with the most oxygen gets the ATE. Okay. So now sometimes there are only 1 oxyanion associated with a nonmetal. So for example, carbon only has CO3. There's not a CO2 with a negative 2 charge. So CO3, so anytime there's just 1 variation, we just get the AT at the end. Okay? So the thing to keep in mind again is the fact that all of these polyatomic ions, they always stay together as a single unit. Okay, and that really comes into play when we're working with them in formulas. So, for example, let's look at, let's build a compound here. Let's say that we're starting with lithium with a positive 1 charge. Now, let's say that lithium, in a typical sense, if we were working with 2 monatomic ions, we would see this, and this is what we're accustomed to at this point. Positive 1, negative 1 cancel out. So let's look at a case where we have, let's say, magnesium with a positive 2 charge. Let's say magnesium is pairing up with a polyatomic ion. So in this case, nitrate. And nitrate is NO3 with a negative 1 charge. Now, the thing to keep in mind here, again, is that as a polyatomic ion, this nitrate will always stay together. The nitrogen and the oxygen will never split, and this negative charge is associated with the entire compound, not just the oxygen. Even though that it's just right above the oxygen, it's associated with the entire compound. So when we build compounds with these polyatomic ions, the beauty of it is that the charges and the crisscross rule, all of that is the same. So in this case, we've got magnesium with a positive 2 charge, nitrate with a negative 1. So when they react, obviously it's going to take 2 of the nitrates to balance out the positive 2 of the magnesiums. But also, the crisscross thing works. So unlike charges, 2, positive 2, negative 1, so this 2 will crisscross down here. And I'm going to back up and do that in a different color so you can see. So this positive 2 will come down here, and this negative 1 will come down here. Now, we don't have to put a 1, it's just understood. So what we end up with is this, magnesium, and then that 1 has crisscrossed down there. And now here's the next kind of special rule with these polyatomic ions. if I just wrote NO3 nitrate and then this 2 that crisscrossed, if I just put that 2 down there like that, that almost looks like I have 32 oxygens there. And I don't need 32 oxygens, obviously. I need 2 nitrates, 2 nitrate groups. So what I have to do is anytime I have a subscript next to a subscript, I need to make sure that I put my polyatomic ion in parentheses, and then this 2 goes outside there. So now this 2 outside the parentheses indicates that I need 2 of this entire group. So I need 2 of these, 2 nitrates, to balance out that positive 2 of the magnesium. Okay, so some other examples of that. Let's look at, say we have aluminum with a positive 3 charge plus hydroxide with a negative 1 charge. Okay, and hydroxide's up here at the top of the list, OH with a negative 1. So here again, we've got unlike charges, positive 3, negative 1. So we're going to crisscross our charges. And we have aluminum, and then the understood 1 that has crisscrossed, and then hydroxide, and now this 3. Now, even though there's not a subscript down here, like there was up here, if we just put a 3 down there as it crisscrossed, that appears, as it's written, actually, it's written that we just have 3 hydrogens. Well, we don't need simply 3 hydrogens. We need 3 entire hydroxide groups. So we've got to put our polyatomic ion in parentheses here to indicate that we need 3 of the entire ion instead of just 3 hydrogens. Okay. So crisscross rule works just the same, except keep your polyatomic ions in parentheses. Okay, so let's look at another case. Let's work with that polyatomic cation, ammonium. Say we have ammonium pairing up with, let's do phosphate. That's a good one. So ammonium, NH4, positive 1, plus phosphate, PO4, with a 3 negative. So when these react, we have the same thing. Crisscross rule works. Unlike charges, positive 1, negative 3. So this negative, or this positive 1 will crisscross and end up down here at the bottom, and this 3 will crisscross and come down here. So we have an NH4, but this 3 has crisscrossed down here now. So we just can't put a 3 right there because it looks like we have 43 hydrogen. So we have to put that polyatomic ion in parentheses. So now when that 3 comes down, it's living outside of the parentheses, and it tells us that we need 3 of everything inside there. Okay, so now phosphate comes out here to the side, and we have this understood 1, and because it's just an understood 1, we don't have to put phosphate in parentheses. It wouldn't be necessarily wrong if we did, but we just don't have to. So this is ammonium phosphate. Okay, so now that brings us to some naming rules when we name these ions with polyatomic ions. Well, it's pretty much the same thing that we've always encountered. So let's say we have, let's just go back to the ones that we just worked with. We had magnesium hydroxide, we had aluminum, it's aluminum phosphate, aluminum hydroxide. Oh yeah, it was aluminum hydroxide up there. Aluminum hydroxide, and then we had, I think it was ammonium phosphate. That's right. I'm getting old, people. Memory slipping. Okay, so now for naming, we simply say the name of the cation. So in this case, it would be aluminum, and then you say the anion. So in this case, hydroxide. And we get those names from our polyatomic ion list. Okay, so then this would be ammonium phosphate. Okay, so now I'll refer you back to our OneNote where we have our practice pages, and this is page 5 in the ion nomenclature list, and it walks you through exactly what I just discussed, the 8 and the ite and the polyatomic ion naming rules. Okay, and then the practice comes on page 6 here, and you should be familiar with kind of this setup here as we've encountered it for the first 2 sets of practices. So the way that I would recommend to do this is like we did before. So for sodium chromate, for this number 1 here, it's asking you to develop the formula for the ionic compound. So sodium is going to be, as always, Na with a positive 1 plus chromate. Now this is where we would have to go to our resource. I'm telling you, you're going to get tired of this sheet, but you're going to be thankful that you have it. So it was sodium chromate. So I have to find chromate on this list. So I search for it, I search for it, I search for it, I search for it, and bam, there it is. CrO4 with a 2 minus. CrO4 with a 2 minus. So chromate CrO4 with a negative 2 charge. Okay, so those are my ions, sodium and chromate. Now what happens when they come together? Well, positive 1 charge, negative 2 charge. So my charges are unlike, so I've got the crisscross thing that's going to happen. So this ends up being sodium with a little 2 down there because it's crisscrossed, and this positive 1 will crisscross down here, but I don't have to put the 1. And it's going to be CrO4, so there's my chromate. And again, it's not technically wrong if you put it in parentheses. If that helps you initially, that'll be fine. Okay. And then at the bottom here, this part is pretty straightforward. This is just you're naming these. So this first one, name the cation first. So in this case, it's the metal is always the cation. So K, potassium is the metal. And then we're going to have to look up our anion. So in this case, CH3CO2. So if I refer to my list, that is acetate. And there's 2 different ways that you can write acetate. It doesn't matter. I typically prefer the C2H3O2. So knowing that that is acetate, we just simply come in and say potassium acetate. Okay. There's one last thing that I want to go over. If you notice here, pay attention to chlorine. Chlorine has 1, 2, 3, 4 different oxyanions. So what that does is it throws a little wrench into our naming rules. So we have some special rules. I want to say for elements with more than 2 oxyanions. So what we see here is we've got ClO4, ClO3 with a minus 1 charge, ClO2 with a minus 1 charge, and ClO with a minus 1 charge. Okay, so now remember, go back to our rules. It says that the one that ends in the ATE is the one that has the most oxygens, and then the next one below that would be the ITE. Well, I've got 4 different ones here, so the question is, which one gets the 8? So in this case, what we encounter is the ClO3 getting the ATE. So we would name this chlorate. And then, like the rule states, the one below this with 1 less would be chlorite. Okay, so that leaves the one with ClO4 and then ClO with no names. So what we have to do here is we have to use prefixes. So ClO4, instead of just chlorate, we add 3 letters, perchlorate. Now what that is, the per, think of the word hyper. In science, hyper always means above or on top of. So literally in this case, perchlorate, we just kind of lose the HY there. Perchlorate literally means above chlorate. Okay, so now ClO becomes hypochlorite. We use the prefix hypo. And the prefix hypo in science literally means below or under. So think of your hypoglycemic, you have low blood sugar. Or if you have hypertension, you have a high blood pressure, so that's above. Okay, so anytime we encounter situations where there are 4 oxyanions for a nonmetal, like chlorine, we have to add prefixes for the top and the bottom ones. And we see that again with iodide. And they each have a -1 charge. This is periodate. This is iodate. This is iodite. And this is hypoiodite. Sounds funny, but it takes some getting used to. Okay, so the last thing that I'm going to leave you with is just to make sure that we're square on these naming rules. I want you to look at these 2 different things here. These 3 different things, rather. What's the difference in all of these? Well, first, obviously, these 2 have oxygens in there. They're all the same charge, but there are differences in naming. Okay, so S with a 2- charge, this is a monatomic ion, remember. So monatomic ions, as an anion, will always end in an IDE. So this is sulfide. Okay, now we have our oxyanions, the polyatomic ions over here. So remember, the one with the most oxygens will end in the ATE, and then the one with 1 less than the most will end in an ITE, sulfite. Okay, so there's a good side-by-side comparison of all of the different names and how they come together. IDE will only be used when it's a monatomic anion. ATE, ITE goes with oxyanions. Okay, so I'll leave you to it, let you do some practice on our sheets in OneNote, and if you have any questions, please let me know and give me some comments and feedback on the videos. So hopefully they're helping out, and we'll see you next round.